open with this 3.1, even though I ignored it the other day. 3.1 is about these imaginary numbers. I mean, here's this idea, you guys. What's the square root of -1? And there is no square root of a negative number. I mean, maybe you've thought about it before, maybe you've never thought about it, but the square root of 9 is 3, because 3 times 3 is 9. But there's no way you can get the square root of -1. What two numbers multiply to be -1? And there is no real numbers that do that, because you know if they're both -1, the answer is -1 times -1 is +1. And +1. So there is no real number square root of a negative number. So we make up, I don't know if we made it up, but we invented, I think mathematicians invented this symbol. For the square root of a negative number, we invented this symbol called I. It's like a symbol. It's like, we refer to it maybe as an imaginary number. That's a little bit of a misnomer. Well, it's not a real number. It doesn't live on the real number line. You know that real number line? We've been talking about domain and range, and when we graph things on the good old X and Y axis, those are real number lines, and no imaginary numbers live anywhere on there. Okay, these guys, they live in their own world, kind of. But let's just see if we can work with them, okay? Let's not worry about where they live. Let's see if we can work with them a second. So can you do the square root of -9? Now you can. I mean, based on this definition that the square root of -1 is called an I, then I think maybe you should think of it like this, you guys. It's a -1 times a 9. And can you do the square root of the 9? Yes. Yeah, that's a 3. And can you do the square root of -1? No. Well, now you can. Wait a minute, now you can. It's an I. So this is a 3I. And I don't really suggest you have to write this, but I'm trying to help you think about it. I mean, really, anytime you have a square root of a negative number, you're going to have an I in your answer. What were you going to say? So basically, you just find the square of the number and then attach an I. Is that? But the I comes from that negative sign, kind of, and that negative sign can be thought of as what generates the I. But the negative sign can also be thought of as a -1. You know, a negative sign. Imaginary number? And this is an imaginary number. Yeah, I mean, we call this an imaginary number. Okay, let's try another one. Can you do the square root of -17? Well, there's not much you can do because you can't do the square root of 17. But you could leave the square root of 17, the square root of 17, but you could pull out the square root of the negative sign. When you pull out the square root of the negative sign, it's an I, and it's out of the radical. The I is not in the radical. The I is out in front. Yeah, and when you pull it out, it's out in front. Yeah, that's kind of all there is to it, except there's a little more to it. Well, like this one, you couldn't do the square root, so you just left it like this. Here's one, you could do the square root of the number, but the negative sign generates the I. So this is where they come from. They come from the square root of a negative number. And they're imaginary numbers, they're not real numbers, and that's where they come from. Now, I want to show you how you can work with them. They're not hard to work with. Are you trying to ask me something? Yeah, go ahead.
Are there other variables in this?
Well, you're right. No. You can sort of pretend I is a variable, but it's not a variable. It doesn't take on different values. What value does it have? That value, which is kind of weird and abstract. But so this I is not a variable. It's this number.
Well, or there won't be like any 9x or the square root of 9x or anything like that.
I don't think so. Here, look at this. So the truth is, we call these things complex numbers, really. And I want to show you something. They come in the form of an a plus or sometimes minus a bi. And then we actually refer to this a as the real part of the number, the real part, and we refer to the b as the imaginary part. Now, and so far in all these examples I did, bless you, there is no real part, I guess. Look at this number. It has the imaginary part 1i. What about this one? It's got the imaginary part 3i. There is no real part to these, I'm sorry. Maybe you could think of it as 0 plus 3i. The real part is 0, the imaginary part is 3. I mean, you can always add zeros anytime you want. Here, where they come from, the reason we discuss these is because we do end up doing the quadratic formula, like I did last class, and we'll do a bunch more of that. And when you do the quadratic formula has that big square root in it, and it's possible for what's under that square root to become negative. And if you get a negative number in a square root, then it's possible that doing the quadratic formula generates imaginary answers or complex answers. Let's do, it's been a long weekend since we saw the quadratic formula, but at the end of a quadratic formula problem, it might look like this. Watch this. Like when you're working on the quadratic formula, I don't know if you remember, but I'm just saying down at the end of the problem, maybe we get to this. Bless you. Now, let's finish cleaning this up here. Watch this. So that's 5 plus or minus, can you guys do the square root of negative 16? It's 4i. It's easy. It's 4i. And it's all over 2. You know what I think I'll do? That 2 is divided into both those terms. Everything is divided by 2. I think I'll just sort of divide that separately. I'll have a 5 over a 2 plus or minus a 4 over 2. What's 4 over 2? 2i. Look, this is a classic complex number like I was trying to describe up here. What's the real part? 5 halves. What's the imaginary part? 2. Actually, these are 2 complex numbers. One of them is 5 halves plus 2i, and the other one is 5 halves minus 2i. These are 2 complex numbers. So they look like this. Here's how you work with them. Watch this. Let's just work with them for a second. If I have 3 plus 4i, and I want to subtract 6 minus 7i, how do you subtract complex numbers? This is a new world. Somebody has to teach you the new rules of this new world. But sometimes they're just the old rules. They're not that bad. You combine like terms. That's a good way to think of it. And even though this I is not a variable, you combine the real numbers with the real numbers, and you combine the imaginary parts with the imaginary parts. Yeah, you combine like terms is kind of what you do. Right? It's easy. Nothing to it. But don't forget, you have to distribute the negative sign. Let me see. So it's 3 plus 4i minus 6 plus 7i. If you combine the 3 with the negative 6, I'm calling that a negative 3. And the 4i and the positive 7i is positive 11i. And there's your answer. It's a complex number. It has a real part and an imaginary part. Check this out. This is the more interesting part of this. What if you wanted to multiply a couple of these numbers? Let's try to multiply. I'll show the same numbers. 3 plus 4i multiplied by 6 minus 7i. Well, if I'm multiplying these things, anybody want to say the word? Foil. Yeah, good. The word might be foil. You multiply, you foil it out is kind of the algebraic term you've learned. I like to just say it's everybody times everybody. I take the 3 times 6, 18. 3 times negative 7, I. Negative 21i. Plus 24i. When you multiply 4i times 6. And now 4i times negative 7i is negative 28i squared. Now here's an important point. A few minutes ago, we said the square root of negative 1 was I. I mean, that was our definition of what I is. Watch this. What if you square both sides? I mean, if I squared this, it would be an I squared. You know what happens when you square this? When you square a square root? Well, you're squaring the square root, so it cancels the square root, and I'm left with what's inside, which is a -1. I don't know how your brain works, but you can work forwards or you can work backwards. Look, if you were staring at this and decided to take the square root of both sides, you could take the square root and I would equal the square root of -1. If you started with this and square rooted both sides, you'd end up here. If you start here and square both sides, you end up here. Anyway, that's a fact, and this is a true, interesting fact, because in this, when I FOILed this out, I got an I squared. And I never leave anything I squared. Nobody ever should, because if you have an I squared, what the heck is it? It's a -1. If you ever run into an I squared, don't leave it I squared. What is it? It's a -1 times -28. So that's actually a positive 28 sitting there. Are you guys okay?
Yes.
I mean, maybe this is brand new to you, but an I squared is a -1. So it's a -1 multiplied by that -28. That's a positive 28, which allows me to add a couple like terms. The 18 and the 28 is a 46. These numbers add up here. These complex, these imaginary parts add up to be 3i, and I'm finished. I FOILed out a couple of complex numbers, and the result is a complex number. How you guys doing? That's kind of an interesting question. To get I cubed, you'd have to multiply by another I, and you would get I cubed. And then you would multiply this by an I, and you'd get a -I. Well, he asked me what I cubed was. So I said, let's multiply both sides of this equation by I to get I cubed. And then I get this -I. Let's do it again. If you multiply both of these equations by another I, you would get I to the 4th. If I multiply this by an I, what would I get? -I squared. Hang on. -I squared. But what's I squared? -1 with a negative sign in front of it. That's just a +1. I to the 4th is just a +1. Hey, I have children, and when my little baby turned 1, I got him a cake and I put this on his cake. Happy I to the 4th. It's just a 1. It confused him though and ruined his childhood. I to the 4th is a 1. Next time you have a 1-year-old baby, you can get this cake. It confused, what it really did is it confused Publix. Publix didn't know what the hell. Couldn't figure out ordering this cake. Listen, this is an interesting little game. I'm not, sometimes, anyway, what am I doing? I'm teaching you a little bit about where a complex number comes from, and then I'm teaching you how to work with it just a little bit. You should practice this in 3-1. There's some homework involving this in 3-1. But that's about it. I mean, why are we interested in imaginary numbers? Because we're studying parabolas, and when we're studying parabolas, we might need the quadratic formula, and sometimes the quadratic formula leads to imaginary answers. I mean, that's really, in the context of what we're studying, that's where they'll show up. In 3.1, they don't put it in context. In 3.1, they introduce you to imaginary numbers, like I just did. Do some My Math Lab homework, practice it. But to me, it's just kind of good exercises. It's kind of interesting exercises working with imaginary numbers. More importantly, I'd like you to know what they mean in the context of our quadratic functions that we're trying to study. So I think I'm finished with this topic. I'm moving on. And let me remind you what we did last week. What we did last week is I would give you a quadratic function like this. Y equals 2x squared minus 3x plus 8. And I would ask you for everything. What's everything? This is a quadratic function. Its graph is a parabola, beautiful parabola, and I want the vertex of that parabola. I want the X-intercepts of that parabola. I want the Y-intercept, and I also would usually ask for the range. The range was always an interesting question. More interesting than the domain. I'll just go ahead and ask you, what is the domain of this function? All real numbers. It's so boring I won't even ask you ever again. Whatever. The domain for all parabolas is all real numbers. You can plug anything into it. But the range is interesting because it gets restricted. The range gets changed depending on where that vertex is and depending whether it opens up or down. Let's get to work on this. Maybe you recall that the vertex formula. Do you recall that? Did you get to practice it? Good. The x value of the vertex is always negative b over 2a. By the way, what is your b?
3.
Actually, your b is a negative 3, but I am going to make it a negative b. By the way, hang on, what's a? 2. What's b?
3.
Negative 3. What's c?
8.
8. Okay. That's a, b, and c. That's those coefficients. That's easy. And this little formula says negative b over 2a is the vertex. It's the x value of the vertex. Okay, what is that? Negative, you said negative 3, or in other words, positive 3 over 2 times 2. Okay, so that's 3/4. Cool. That's the vertex?
No.
Yeah, I don't really say that. It's the x value of the vertex. Listen, it's half the vertex. The vertex is a point, and we just found the x value, 3/4. How do I find the y value?
F of x equals negative b over 2. Plug in 3/4.
That's right. To get the y value, you plug in 3/4. You plug 3/4 in. To get the y value, you got the x value. I guess you really don't want to make a mistake on this x value because this x value dictates what the y value is. Once you find this x value, to get the y value of the vertex, you have to plug it in. 2 times 3/4 squared minus 3 times 3/4 plus 8. Hey, 3/4 is a nice little decimal. You could change it to 0.75 and do the same thing, a little easier perhaps, with a calculator and a decimal. It might work out easier. I'll just show you how to work with these fractions though for fun. I like fractions. Do you know how to square a 3/4? Square the 3/4. 9/16. Good job. It's going to be multiplied by 2. You know what? I think I'll cancel that 2. I think I'll have 9/8. Is that okay with you? I just canceled a 2. Whether it's okay with you or not, I did it. What about over here? Multiply fractions, 9/4 plus 8. So now look at me. I got to add up all these numbers. I need a common denominator. I mean, it is 8. Oh my goodness. Oh my goodness. What's this then? 9/8. What do you have to do? Multiply him by 2? 18/8. Thank you. Negative 18/8. And what do I got to multiply him by? I got to multiply him by 80. 64/8. I'm going to add up those numerators and I get negative 9 plus 64. 55/8. Thank you very much. Wow. Like I said, this is the part of the class where nobody likes adding up millions of fractions. You can pick up your calculator. Sometimes your calculator will do your fractions for you, I suppose. But like I said, it sure is smart to use that. I mean, plug in 0.75 and let the calculator do that for you. I guess this answer in decimals is what?
6.875.
6.875, yeah, 6 7/8, I guess is what it is. 6.875. Anyway, or 55/8, same thing. So you might call that a tough vertex, right? It didn't come out to be 3 and 2. It came out to be 3/4 and 55/8, you know? Or 0.75 and 6.875, you know? It's a little tougher vertex than your old baby algebra vertex. This is college algebra vertex. Yes,
So
sir.
why did you change that to 0.75, the 3/4?
Well, 3/4 is 0.75. They're the same thing. I said you can do that, and you can use 0.75 instead of 3/4 is what I said. It'd be easier. It'd be easier than messing with all these fractions, right? But in case you're sort of a fraction freak like me, I thought I'd help you with some fractions. Hey, let's do this. Let's keep going. Let's skip over. The hard part is always the X-intercepts. We'll skip over those. How do you get a Y-intercept? You plug in a 0 for X, and what do you always get? Bam, bam.
C.
You get that number. Yeah, you call it C. Yeah, it's 8. Yep. And you know what? Based on those couple ideas, I can get a good graph. I'm going to start with a good graph here. The vertex is 0.75. If that's 1, then here's 0.75. And then what do? Go up. Where's the Y value? What's the Y value? There's the Y value. Again, I'd rather have a decimal, right, a number, thank you, which I got. It's 6.875. I'll do that. I'll go up 6.875, right about there. I'll call that a 7. This is 6.875. Hey, what was the Y-intercept?
8.
8. That's kind of interesting. Does this parabola open up or does it open down? So here's the vertex. It goes through that Y-intercept, and you guys just told me it opens up, which makes sense. If that's the vertex and that's the Y-intercept, I think I'll try to draw this. Are you guys with me? You see how easy that is? I labeled that 7, but I really maybe should label this. What is this? 6.875, right? Right. There's this X value here, 0.75. That's kind of a line of symmetry. That 0.75 kind of cuts the parabola in half. They call it an axis, or an axis of symmetry. The vertex was pretty easy, except for some fraction work. Okay, again, I keep saying decimals avoid fraction work. Y-intercept sure is easy. These X-intercepts are always a little tougher. I can go work on these X-intercepts unless y'all got an idea.
There won't be any.
There won't be any. What's he saying?
There's no.
He's looking at the picture. He's looking at the picture and he's realizing, look at it. If it lives up here and it opens up, what's the X-intercepts? Right, look at it. Right, you've got an accurate picture. Now, if this guy was upside down, would there be some X-intercepts?
Yes.
Yes, there would. Right, but this guy, he lives up here. He opens up. He just saved himself a ton of work by saying, hey, look at the picture. There are no X-intercepts. Listen, don't leave it blank, though. What should you put?
None.
None. Or for emphasis, you could put ain't none. Wait a minute. Ain't none is like a double negative. That means there is some. You know what I mean? You can't have a double negative. I mean, ain't none. That's just ain't right. How about ain't none never? That's a triple negative. Just none would be good, actually. None. Hey, what's the range? We could have answered that 10 minutes ago, maybe 5 minutes ago. I can look at the picture. Once I add the picture, I can definitely answer the range question. The range is? Good. I think think I heard the right answer. It's all those y values greater than or equal to 6.875. It's, that range is always dictated by the y value of the vertex. That's 6.875 in case you forgot. Yeah, you know, it's either above it or below it. It depends, again, whether the parabola opens up or opens down. Good, we did good. Now I want to do a little more with this. I'm going to erase this stuff here. Let's say I was looking for these x-intercepts. Let's pretend you didn't observe this fact. Like pretend you were just working, and you weren't graphing yet. And so you might have thought, let's go find the x-intercepts. I want to show you what happens. So how do you find the x-intercepts? You let y equal 0, and all of a sudden you're solving a quadratic equation. And this is what, you know, this is the main thing you got to practice, I guess, solving a quadratic equation. I could work on some parentheses. I could work on trying to see if it factors, but it doesn't. But depending on how good you are at factoring, it might take you a while to decide whether it factors or not. I'm just going to, let's say it doesn't factor. If it doesn't factor, I'm going to use the quadratic formula. Here I go. Do I have to sing it for you again? Thank God. All right. The quadratic formula, negative b, which by the way will be a 3. Negative b will be a 3. Plus or minus the square root of b squared. That's going to be negative 3 squared. If you don't mind, can I just say 9? It's a negative 3 squared. Some students do that wrong. A little time out here. It's negative 3 squared. If you type that in your calculator just like that, your calculator is going to tell you negative 9, which is wrong. It's a negative 3 squared, which we all should know is positive 9. Yeah, yeah. So it's a 9 minus a 4 times a times c, all over 2 times a. You guys okay? Got my a and my c in there. My a. There it is. Let's keep working on this. What you usually have to do is clean up what's inside that square root. And what is inside that square root is 64. 9 minus 64. I multiplied those 3 numbers. That's 8 times 8. And 9 minus 64 is that negative 55 all over 4. So look at this. You got an imaginary answer. And that's why there are none. That's the connection. That's the real connection of imaginary numbers that I'd like you to make. When you're working on the quadratic formula and it leads you to a negative number under the radical, that means you know your answers are going to be imaginary. And what does that mean in terms of x-intercepts? There are none. You follow me? To me, that's the important part of, that's the knowledge of imaginary numbers I'd like you to know. In 3-1, you can work with imaginary numbers. But I'd like you to know what they mean when they come up in a problem like this. It means there are no x-intercepts. Right. So as soon as you see the negative number, you can come over here and say, nope, there's no x-intercepts. I mean, I guess you don't really have to finish this problem. If you were to finish it, there's not much really to do. 55 is 11 times 5. That doesn't clean up at all. I mean, how can you do any more cleaning on this? You could pull out the I. You could do that. That's about it. So you could say it's 3 plus or minus I square roots of 55 all over 4. Those are your imaginary answers, which means they're solutions. What's funny is they're solutions. They do make this equation equal 0. They do. They are the solutions that make this equation equal 0. So they're solutions. They're called roots maybe, or zeros of the function. They're called zeros of, but they're not real numbers. They're imaginary numbers. So they don't show up as x-intercepts. They're not x-intercepts. That's what I want to say. They're solutions, but they're not x-intercepts. Let me say that. They are solutions. Maybe even I'll say call them imaginary solutions, but they're not x-intercepts. Hey, do a good word problem, I think. But this was good. There's a lot of good word problems involving quadratic functions. One of them is this. I brought a little ball in here today. Listen, I should have brought a basketball, but anyway, watch this. Anytime you throw an object up in the air, watch what it does. Well, first of all, what did it do? It fell down. Gravity pulled it down to Earth. But before gravity, while gravity was pulling it down, gravity's kind of what made it take on that shape. Did you see that shape? What was that shape? It was a parabola. Here, you don't blame me? Put on your safety glasses. No. All right, anyway. Oh man, each bounce is a parabola. Look at that. Parabola, 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 parabola. There's millions of parabolas. It's beautiful. It is true. Throw a baseball from left field in, it's a beautiful parabola. Hit a baseball, shoot a free throw, it's a beautiful parabola. All these things that go flying through the air are parabolas.
Home runs.
LeBron James is an expert on quadratic form. I don't know. But listen, let me say something. I was sort of launching it sideways. The truth is, the problems we work with, we kind of just throw the thing straight up. But even if it's straight up, it's a parabola. Watch this. Doesn't look like a parabola. It looks like a straight up and straight down, right? If you plot its height as a function of time, it's a parabola. Even though it looks like its path is just straight up and straight down. Let me show you what I mean. See, gravity is an acceleration. So it causes it to speed up as it heads toward Earth. Well, and as it heads away from Earth, it caused it to slow down. I mean, if there wasn't gravity, what would happen to this thing? It would just keep going. So gravity slowed it down and caused it to actually stop for a second up there. I don't know, can you see it stop? Watch. For a second it stopped. Less than a second. For a moment, for an instant, it stopped. And then gravity accelerated it back to Earth and it sped up on its way back to Earth. And when you plot its height as a function of time, here's what I want to say. I'm throwing this up at a certain initial height. I threw it up, so that first second, it went up kind of far, maybe. What happened after the second second? It probably didn't go up as far, did it? It probably went up a little less distance, don't you think? Gravity's slowing it down, you think? Maybe it reaches its peak after the next second, maybe. Then what does it start to do? It starts to come down, but after that first second it comes down, it doesn't go too far, but it starts to speed up. So what happens after the next second? It comes down a little further. What happens the next second? It comes down quite a bit further. Are you following me? I know it. I'm plotting its height as a function of time, and I'm saying every second it does different distances because it's speeding up and slowing down, or slowing down and speeding up. And it creates a parabola. Okay, good. I'm glad you're convinced. So then we give you this equation. And we tend to use the letter S. I'd just assume use height. I'm going to call it h of t, but I want to tell you that sometimes the book uses an S for height. But I'm going to say it's h of t, and I'm going to use t instead of x. Is that okay with you? I'm going to use t because I have a time as my time axis. And here is an equation. Negative 16t squared plus 32t. I'm sorry, let me change that, please. 64t plus 125. And that's the equation for a word problem. I might make up a word problem, and I might make up a word problem that says this. I was standing on top of the library, 125 feet above the ground. I threw a baseball up in the air with an initial velocity. That's just the initial force I threw it up with an initial velocity of 64 feet per second. Do you see those numbers in the problem? Mm-hmm. Yeah. That 125 is sort of, you know, it's fun to, you know, this is a word problem, and it's fun to think of the reality of the word problem. But simultaneously, I think it's cool to think of just good old parabolas like we studied 10 minutes ago. But I mean, the reality of the word problem is one thing, and then there's just the good old math. Let's get back to the good old math a second. If this is a parabola, what's his y-intercept? 125. Does that make sense? I'm standing on top of the library, 125. That's where I start. That's where this problem starts. And then I threw the ball up in the air. You follow me? So the y-intercept of 125 is that initial height, the starting height. And then I threw it up with a certain speed of 64. That speed gets multiplied by the time. This other number is this negative 16. It turns out that that's half of gravity. I told you gravity's working on this thing, and gravity's pulling it down. Maybe that's why it's negative. Remember, I threw that thing up. Maybe that's why that's positive. I threw it up, right? But gravity's pulling it down. That's why that's negative. All these problems will have a negative 16 in them because if we're on Earth. I could do another word problem where we're on Mars. If we go to Mars, this number will change because gravity's different on Mars. I'm not trying to get complicated. I'm trying to sort of explain these numbers, but you don't really have to know too much about these numbers to answer this question. This is a parabola. It starts at 125 feet. I threw this ball up. It's going to come up here. It's going to come down here. Here's what I'd like to know. Here's the question. When does it reach maximum height? And then here's another question. These are classic questions. What is the maximum height? And I know that they sound like scary word problems, but can somebody tell me how unscary this is? This is totally easy. When I ask for max height, or when does it reach max height, or what is max height, when you think of maximum height, and you're thinking of a parabola, what are you thinking about? The vertex. Beautiful. I mean, this is just me asking about the vertex again, ain't it? I mean, isn't it? This is just me asking about the vertex, and I mean, that's all it is. And it's set in a word problem, and word problems tend to freak students out. You guys seem nice and calm. I appreciate that. You shouldn't be freaked out. It's just a vertex. Wait a minute. Is this the vertex or is this the vertex? Or
What is when is behind? So that'd be here.
the vertex, if you remember, is two parts. It's the x value and the y value. Well, I think I'm asking for both parts. Now, in this problem, the x value is what in this problem? It's not x, it's, well, t. The x value is the t value, and the t value is time. And so when somebody uses the word when, I think we're looking for I think this is the time it takes to reach maximum height. I think that's the The x value of the vertex. Can you read that and understand that? That's the x value of the vertex. Then this one wants to know what actually is the max height. And the max height is actually a y value, don't you think? So can y'all read these and say, this is the x value of the vertex, this is the y value of the vertex. That's your job. Can you read these and understand that? I hope so. That's all it is. Let's do it. The t value, it's the x value of the vertex, but it's the t value, and it doesn't matter. I mean, it's t. But what is it? It's that negative b over 2a. This is very easy, you guys. Negative b is negative 64 over 2 times a, which is 2 times negative 16. This is a nice one. I put some nice numbers in here. What is that? Two. Thank you very much. 64 divided by 32. It's a 2, right? 64 divided by 32. It's a 2. 2 seconds. That's the answer. When does it reach max height? 2 seconds. If this is my picture, it's not a bad picture. At 2 seconds, it reached max height. At 2 seconds, it reached max height. What is the max height? Oh, that's the y value. How do you get the y value? You plug in the 2 into the function to get the y value of the vertex. You plug the x value into the function to get the y value of the vertex. That's negative 16 times 2 squared, 64 times 2 plus 125. You know, it is easy. Plug a 2 in. It's easy. But it takes some work, and people make mistakes. People forget to square this one. They forget to square this one. That kind of ruins it. There's a lot of things you could do to ruin it. So take your time and practice it. That's a 4 times 16. I think that's a negative 64. This is a positive 128. That's 125. If you add these numbers up left to right, y is what? What did you say? 189. Is he right, you guys? 189 feet. That's the answer. Woohoo! That was fun, wasn't it? Okay, let's do the not fun stuff. You ready? Part C. When does it hit the ground? Okay, well, it said when. When it says when, I try to do this. If it says when, I think it's looking for a time, the time it takes to hit the ground. On my picture, oh, by the way, what was this y value up here? Oh, that was the 189 feet, right, you guys? Yeah. Anyway, on my picture here, we got a good looking picture. Here it goes. Anyway, it comes back down to Earth. According to my picture, it looks like it's going to hit around 5 or 6 or 7 seconds. But my question is, when does it hit the ground? I want the time it takes to hit the ground. When does it hit the ground? What should you do? Oh, he's saying that's just another word for X-intercept. Is he right? Yes. Hitting the ground is, thank you. See, I guess I'm doing the same old thing, except I'm in a word problem. I'm finding the vertex and I'm finding the X-intercepts. Exactly. But I'm in a word problem instead of a math problem. Yeah, you're right. If I want to know when it hits the ground, that means the height is 0, and I should solve this equation. Now, here's the problem. I got some big old nasty numbers. A calculator can sure help me with this. But I think I got to do the quadratic formula on this. With big old nasty numbers, nasty quadratic formula. But I ain't scared. Are you scared?
So it's 64.
All right, here we go. It's negative b, so I guess it's negative 64 plus or minus the square root of 64 squared. I'll work on that in a minute. Minus 4 times a, what's a? Negative 16 times c, which is 125. I got to multiply all that stuff, you guys. All over 2 times a. What's 2 times a? Yep. 2 times negative 16. If you don't mind, I'm going to put negative 32. And then I pick up my calculator and I square 64. And let me ask you, this is where people make mistakes. Am I going to be subtracting here? It says I'm subtracting. But I'm subtracting I see a negative number coming up here. So subtracting a negative, I'm going to end up adding this, right? Do you see that? I like to just sort of count up the negative signs. You see 2 negative signs? Then you're going to add this.
Yeah.
You see 3 negative signs? You're going to subtract it. You see 1 negative sign? You're going to subtract it. You see 4 negative signs? You're going to add it. Right. Here, let's do it a little slower here. I'm running out of room. I'm going to back up over here. The answer is negative 64 plus or minus 64 squared.
4096.
Thank you. I don't know if I trust that. 64 squared. 4096, she said. 4096. And then I'm saying it's plus 4 times 16 times 125. 8,000. Plus the 4,096. Hang on. That's going to be negative 64 plus or minus. When you add that up, it's a big nasty square root. It's 12,096 inside the square root. Are you guys okay? And then finally, this is a word problem. Now you've heard us, we've had arguments about when should we be exact and when should we just pick up a calculator. This is a word problem. I want to decimalize this. I do not want to try to work with this exactly. I would decimalize, I would pick up my calculator and do this. What is the square root of 12,096? It's not perfect, I don't think. Is it? What is the square root of? No, it's not perfect. It's 109.98. So I'm going to write that. Out of the square root, it's a 109.98. You can almost call that 110, I guess. But you don't want to round too much. But you guys with me on this? Hey, we're almost done. There's 2 answers here. One of them is negative 64 plus that number divided by negative 32. The other one is negative 64 minus that number divided by negative 32. There's 2 answers, right, you guys?
Yeah.
Let me see. Negative 64 minus that number, and then, be careful. I'm going to hit enter, and then I'm going to divide the whole thing by negative 32. And I just got a 5.44 seconds. That was the minus. That was this guy minus this guy, and then divided by a negative number. I guess that ended up positive. Here comes my next one. Negative 64 plus the 109.98. That ends up with a positive number, and when I divide by negative 32, I get this little negative answer, negative 1.44. Be careful. You should be practicing this. You can practice it later, or you can practice it now, or both, later and now. But, you got to be able to execute this on a test in a couple weeks. It's not that hard, but you should practice it because you can make mistakes in that process. But we're done. And I got 2 answers, but there is really not 2 answers. It hits the ground. There's only one answer when it hits the ground. And it's the positive one. We should pick the positive time. The negative time we should just toss out. It's just not, it's not the answer. Well, I'll tell you what that negative time is. This is a parabola, and it does have 2 X-intercepts. If we got out of the real world situation, if this parabola extended down here, look you guys, if this leg extended down here, it would cross, and guess what that X-intercept would be? Negative 1.44. Right, that's what it is. But for this real world problem, that answer is irrelevant. we toss it away and we circle the correct answer. There's only one correct answer. That's awesome. When does it hit the ground? 5.44 seconds. My graph's a little off here. My labels are just a little off. Now it looks better. 5.44 seconds. Any questions? I mean, these numbers are big and nasty, and you might think, wow, that was hard. But you do get your calculator in your hand, and you just need to don't make mistakes. Watch your positive and negative signs. Use your calculator wisely, and get the correct answer. I've been warning you, sort of, I guess. Chapter 3 gets harder. I guess I've been sort of saying that. Now we're here, and maybe you can tell, yeah, it's harder. Maybe you think it's not. I don't know. It is. It's a little tougher. There's plenty of places to make mistakes, even if you're an expert. If you don't practice it much, you can... Test grades tend to go down a little here in Chapter 3. But not if you say, hell with that, and rise to the occasion. You don't have to go down. You go up. Hey, I think I got another question for you. Ready for this? Here's another question. Part D. Same grid, Part D. And then there's an E and an F. No, let's just do a D. Hey, there's a bird. There is a bird. There is a bird. There was a bird. Flying around at about 160 feet above the ground. You know what the question is? I haven't asked it. You know what the question is going to be? When does it hit the bird? When does the ball hit the bird? Poor bird. I mean, I like birds, but I need a word problem. I need a good word problem. I'll sacrifice a bird for a word problem anytime. So there's a bird flying around. You get it? Where's the bird? The bird's flying around at 160 feet. Is that what it said? So where is that? Oh, right about here somewhere. Yeah, somewhere it's 160 feet. There's a bird flying around. So I could possibly hit the bird, right? I could possibly hit this bird, I guess. If I get the right angle. So how do I answer this question? When does it hit the bird? See, when I said, when does it hit the ground, what did we do? The ground is a height of 0, and so what did we do? We plugged in a 0 for the height. Now check this out. When does it hit the bird who happens to be at 160? I guess I should plug in 160. I mean, my question a minute ago was, when is this height equation equal to 0? That was the ground. Now my question is, when is this height equation equal to 160 in order to hit the bird? So now I'm solving this quadratic equation. Now listen, we should do this. I don't think we've practiced this much, and I don't even know if I've told you this. But for any quadratic equation, to get started on a quadratic equation, you want it to equal 0. And right now, I set it equal to 160. So what's step 1 of solving this quadratic equation? Move the 160. Thank you. I mean, you set it equal to 160 because that's what the problem asked. But now, to do the math, you subtract the 160. You get it equal to 0. All right, hold on. I subtract the 160. That means I subtract the 160. This is a negative 35. This is a t. And now I'm solving this quadratic equation. Solving this quadratic equation will lead to this answer. When do you hit the bird? Or in other words, what time is lunch? No, that's gross. Yeah. Chickens don't fly that high. Chicken can't fly. All right, quadratic formula. Again? You getting sick of the quadratic formula? We just got started in chapter 3. You got to knock out the quadratic formula. Here, I'll race you. On your mark, get set, go. The quadratic formula, t equals negative b plus or minus, that's a 64, plus or minus the square root of 64 squared minus 4 times a, which is negative 16, times c, which is a negative 35. That's interesting, all over 2a. There it is again. The main problem is working inside this square root. I get that 64 squared again, don't I? What is that? That's 64 squared. That was that 4,096. And then this is going to be, look at those 3 negative signs. See them? It's going to be subtracting whatever that number is. But this time it's subtracting instead of adding, I guess. 2240. All over, negative 32. I'm going to subtract that. After I subtract it, what am I going to do?
Square root.
Square root it. Right. It's in I want to get it out of the square root. I'm going to take the square root. I'm going to subtract it and take the square root. Can you do that for me? Subtract it and take the square root, and what number comes out?
40.
What'd you say?
43.08.
43.08. Is she right, you guys?
I hope so. Yes.
She subtracted it, and then she took the square root and got this number. And it's out of the square root now. You guys all right? All right, we're almost done. I hope she did that right. She subtracted it?
Yes.
She took the square root. All right. Good, thank you. And now we got 2 answers. Sometimes this is hard for people right here. It's negative 64 plus that number. I would hit enter and then I would divide. Or I would use, maybe I'd use parentheses around my numerator. You just, negative 64 plus that 43.08 equals that. And then when I divide by negative 32, I'm getting this little answer, 0.65, oops, 0.65375, I'll just call that 0.65. 0.65 seconds. You guys okay? That's a 6. What's the other one? The other one is negative 64 minus the 43.08, and then divide that by negative 32. 3.35 seconds. You know, last time I was trying to hit the ground. And when we hit the ground, we only had one good answer. The other answer we threw away. But this time I'm trying to hit the bird, and I think both answers are good. This poor bird ain't got a chance, boy. If I miss him on the way up, I might hit him on the way down. You with me? Both answers are good. On this, there's two chances to hit the bird. When do you hit the bird? Well, you got 2 chances. On the way up or on the way down. Yes, ma'am?
Does that take into account how fast the bird is moving?
You know, there's a lot of stuff not taken into account. One thing is we're ignoring wind resistance at all. Of course, a baseball flying through the air doesn't have much wind resistance. But anyway, we're ignoring a few physical phenomena. And so this bird is just sort of hovering above my head, I guess. Yeah, he's in hover mode. He can leave. Anyway, in order for me to hit him, he better be right over my head at 0.65 seconds. If he happens to be just off to the side, then I miss him. I'm just pretending he's hovering right above my head. I don't know how he does that. He's a hummingbird. Maybe he's a hummingbird. Which is not good eating, but go ahead.
Only in the word problem do we take the number out of the square root? Or can you do it in the regular problem?
This is a good question. I have this discussion with students a lot, and like if this is a math problem of some sort and we end up here, I might like you to simplify it more. And so I don't really want a decimal. I think I want this simplified. So how do you simplify the square root of 12? 2 square roots of 3. I think that's because you make it 4 times 3, and then that's all over 5. Nothing cancels. We're done. We're finished. And so we simplified this, and we did not decimalize it. And I think that's appropriate when it's just sort of a math problem. And when it's a word problem, let's go ahead and get some decimals, because I want to know the time. You know what I mean? I want to know these. I want to know.
Okay.
Yeah. So that's my answer.
Nice words.
Math problems, we tend to leave exact. Word problems, let's pick up our calculator and we're rounding off. These are rounded off decimals. They're not exact, but they're good enough for the word problem. Right. Hey, watch this. Question E. This is an easy one, though. Hang on, don't freak out. Question E. There's a bird flying at 200 feet above the ground. When do I hit the bird now? Good. Back to my picture. If he's flying at 200 feet, when do I hit the bird? Never. It kind of got to go back 15, 20 minutes and realize that your maximum height was 189 feet and you're not going to be able to hit that bird. Right, that bird's safe. That first bird should have learned that lesson. Yeah, so sometimes there might be an easy answer. You don't have to do a bunch of math if you're paying attention. You don't have to do any math here. The answer is never, right? Yes?
On your test, will you have the graph or do we have to draw the graph?
Yeah, I usually don't give you a graph. And for this word problem, you don't really need the graph. As a teacher, I think the graph sort of helped you understand things. And as a student, it might help you. You know, real quick, when you read one of these word problems, you can quickly do this. You guys, listen. Do you know where this problem starts? I mean, I erased the original word problem, but I was 125 feet on top of the library, right? So you can roughly go like this on your piece of paper. You can say he threw the thing up. Did I throw it up? Well, then you can just kind of roughly do that. And that is the picture of what's going on. I don't know all the details until I start doing the work. After I did the work, I realized that 2 seconds was the maximum height. The maximum height was 189. I started filling this stuff in after I did the work. But just to start the problem, this little picture could help you think. And this is the picture of throwing something off a building. This is the picture. This is time, and this is height. Okay, I'm going to quit.